Hello, class. Here's an overview of the third lesson in Module 7. Now, rather than doing an overview video and then a short lecture video, I'm combining them in one. So first, let's talk about the overview part of this lesson, and then I will briefly mention the differences between the tests. Okay, so the overview, two-sample t-test. Well, we have discussed one sample t-test for a population mean, but sometimes we'll have two samples come from two different populations, and we are interested in comparing the population means. And we will use a two-sample t-test. So the objectives of this lesson are to distinguish between the paired and unpaired two-sample t-test, and then to conduct two-sample t-tests in R. All right, now for the discussion. So we have a random sample of size n from a normal distribution, mean mu sub x, standard deviation sigma sub x. Then you see we have a random sample. I'm calling these y's, but size m, normal distribution, mean mu y, standard deviation sigma y. And what we want to know is mu x equal to mu y? What that means is throughout the two sample t-tests, our null hypothesis is exactly this, that mu x equals mu y. And I will discuss where our alternative hypothesis is that the two means are not equal. Okay, well, we have seen t-test from the first lesson in this module. This is in R. There are really three possible tests that I'm going to give an overview on. One is a paired t-test, and in R, the differences here is we will use this option, paired equals t. We will have what's called a Welch t-test, and then we will have a t-test with equal variance, and in R, we just have this option. So these two are unpaired, as we will discuss. So first case, paired two-sample t-test. So we can use this when n equals m. It means the two random samples are the exact same size. So maybe you have 50 observations here and 50 observations here, something like this. Okay, so specifically, we have x1 through xn, y1 through yn from these two different normal distributions. Well, what we can do is define this d sub I. You can think of this as the difference. Take xi minus yi. Okay, so then d1, d2 through dn is a random sample from a normal distribution, and the mean will be exactly just the difference of the two means. All right, so once we have this single sample from a normal distribution, our original null hypothesis, that mu x equals mu y, is equivalent to this null hypothesis. So this is our null hypothesis, mu d equals 0, and the alternative is this mu d is not equal to 0. And so this paired t-test, it's really just a one sample t-test, which we learned about and practiced in lesson 1. Okay, that's the nicest case. That's the best case possible when the random sample, or each random sample, has the exact same number in it. Okay, but in the unpaired case, this would be when n and m are different. Really, we have two possibilities. The one we're going to use more often is this one. It's the Welch two-sample t-test. Now, let's think for a moment here. Naturally, we would reject this null hypothesis when this statistic, so sample mean of x minus sample mean of y, is far from 0. Well, this random variable, x bar minus y bar, this will have mean mu x minus mu y. Just thinking linear combination of the random variable x bar and the random variable y bar. Moreover, what is the variance? we assume that the x's and the y's are independent. And this would give that the variance, well, the variance of x bar is sigma x squared over n, and the variance of y bar is sigma y squared over n. And because we are assuming independence, we can use properties, over m, we can use properties of linear combination. Okay, therefore, under the null, which is here, this x bar minus y bar is distributed as follows. Normal distribution means 0, and standard deviation, well, I'll write it this way. Standard deviation equals the square root of this. So the square root of exactly this. Okay, what would be our test statistic here? Well, we don't know sigma x or sigma y. And so our test statistic would be this x bar minus y bar over here. This would be this estimated standard error. We take the square root of, well, instead of sigma x here and sigma y here, we put the sample standard deviations. Well, this looks beautiful. However, so this does not follow a t-distribution exactly. So this approximately follows a t-distribution with, well, a fractional degrees of freedom, which is very intricate looking. Fractional degrees of freedom. Well, the good news is we have R to actually do our calculations. Okay, the third case, here N and M are not the same size. Unpaired. Once again, we have this assumption that the x's and the y's are independent. Well, if you are in the beautiful situation where the variance of x equals the variance of y, population variance, we can get an exact t-distribution test statistic. So this one is just approximately a t-distribution. But if the population variances are equal, we get an exact t-distribution. We have to define this, which is called the pooled variance. It looks intricate. The way to think about this is kind of a weighted average of the sample variances. For example, let's suppose the sample variances are physically equal. Sx squared equals sy squared. Well, then you notice you would just factor out this common sample variance, and you would have n plus m minus 2 over n plus m minus 2. You would get this common sample variance here. But most likely, even if the population variances are equal, the sample variances won't be. And so this is a sort of weighted pooled variance. And then under the null hypothesis, we take x bar minus y bar divided by, here we have this pooled sample variance, and underneath this radical, this will follow a t-distribution exactly with n plus m minus 2 degrees of freedom. And the two-sample t-test with equal variances is based on this sampling distribution. Now, my careful in red is important. So careful. In order to use this, the sigma x squared must be equal to sigma y squared. Now, how are you going to know this in reality? All right, is required. We can test for this using an F-test. And I have the details of the F-test built into one of our Canvas pages. But without the F-test, you can't run this because this two-sample t-test with equal variance requires that the population variances are physically equal. And so it's a lot more common. Maybe I will also write this. The Welch test is a lot more common and is usually a better one because of this strong requirement of having equal population variances. All right, so I wanted to give this overview of really the three different two-sample t-test. Paired, which is wonderful, but requires that the sample sizes are equal, and then two different flavors of the unpaired. And usually we use the Welch t-test because of this extra requirement in the two-sample t-test with equal variances. Thank you so much, students. At this point, you can work through the Canvas pages to practice the two-sample t-test and also read about this F-test and run this in R. Thank you.